Hi, I'm Michael Jacob, and my partner is Sandra Kobla, and our work this summer was on the 3D anisotropic scattering transform. So the scattering transform is a statistical method similar to the power spectrum that produces summary statistics for a field. So how it works is you have a set of filters, which are wavelets, and you perform iterative convolutions of the field using those wavelets. And so the end result is a altered field of which you take the spatial average, and through iterations you get multiple scattering coefficients, which are the summary statistics for the field. So as opposed to other methods like the power spectrum, this can help yield non-Gaussian information and local interactions. And a lot of research has been done into the 2D scattering transform, but not as much in the 3D version, and specifically in capturing directional dependencies within the field.
So how exactly we did this was we used a mathematical method to take the wavelets that are already directional in 2D and map them onto 3D surfaces. That mapping resulted in the figure we see in the bottom left, and the alternating of colors is the directional property there. So that's the wavelet that we now used to do the rest of our scattering transform through our results.
Right. So the first thing we wanted to test is how well our wavelets could perform on non-directional data. And in figure two, you can see the bottom left is our predictions of the energy of quantum molecules, and the top right is existing predictions using non-directional wavelets. The bottom right figure shows the disagreements and agreements, and the blue is in where our wavelets are in agreement with existing. So you can see that on non-directional data, our wavelet performs at a similar level to existing ones, which tells us that it does function as a wavelet and has all the key properties we need to perform the scattering transform.
Now, after we proved that our wavelet works just as well on non-directional data, we extended our analysis to directional data. We first performed an analysis of the large-scale structure from the Quixote simulation using Fisher matrices. We took our wavelet and ran a scattering transform through different cosmological realizations in the simulation. And then we demonstrated the S8 omega matter tension through figure 3 in the middle of the poster. Our analysis is able to well constrain the cosmological parameters S8 and omega matter and does perform better than the power spectrum, showing that we do capture directional data. Additionally, we do image generation using our wavelet, where we perturb a random field until it matches the scattering coefficients of a new field. And by doing this, we're able to create fields similar to an original field via the scattering transform. This generation is still a work in progress.